I called this explosions and other problems. You know what? If I've done my job right, all this is going to be, Neve, is dotting I's and crossing T's, but nothing new in the alphabet, if I've done my job right. So, example 1 says this. A 10 kilogram, when I told you, I apologize, these questions are repeats. Let's make that a 12 kilogram stone. Is sliding along the ice when it hits a stationary 20, that's a 20 kilogram bucket of sand. After the collision, the curling stone's velocity is, let's carry on with our theme of just adding 2 to everything, 5 meters per second east. And the bucket has the velocity of, now I got to be a little careful here. I'm going to go 3.3 just on the off chance because I need to make sure I don't demand more kinetic energy than was in the initial collision. I want to make sure I don't make up something impossible. At 40 degrees south of east. What was the initial velocity, magnitude, and direction of the curling stone before the collision? This race is probably tougher than I'll throw at you on the test in that I think, I'm going from memory, but I'll confirm, I'll probably photocopy the test this weekend and take a close look at them. I think I gave you a diagram much more like that, or much more like that in every question written section on the test. But it's good practice for us to see if we can recreate the whole thing. I think I would start by going, hey. All right, talk me through this. Talk me through this. Really? Ooh, some of you in trouble. How do I know that I should start with conservation of momentum? Well, then let's start by going the sum of all the initial momentum equals the sum of all the final momentum. Right? Before the collision, what's moving? The stone, the bucket, or both? Momentum, I'll use S for stone initial. Wham, they collide. After the collision, what's moving? The stone, the bucket, or both? And I hope, Petra, if I've done my job right, if this is becoming repetitively boring, this first stage, then I've done my job right, and we can kind of say it's become a habit. I hope. So this is our stage. Hey, what's moving? I think both, and I think separate. Yes? So we have momentum of the stone and momentum of the bucket. Okay. Looks like, well, what are they asking me to find? What are they asking me to find, Josh?
Read the question.
The initial velocity.
Of? You know what? That's what they're asking me to find. Actually, that's not too bad a question, I think, because then I should have two vectors that I can clearly add together tip to tail. Looks like the stone's velocity after the collision is due east. How big is that? And again, I think I said this last class, but it bears repeating. I've been helping some kids after school, and it's ironic. The kids that are coming in for help, because they're struggling, are the ones that aren't drawing this little picture. This is it takes 5 seconds, but this cuts down on so many mistakes because you're looking at carefully each vector individually, and you're doing the momentum calculation right now. I find when kids did the momentum calculations on the actual triangles, they put them in the wrong place. They did stupid calculator mistakes. Because most kids, if they go can you go mass times velocity right now? What's going to go here? What's the mass? 12. What's the velocity after the collision? 5. I would argue, Cliff, that you can probably do that in your head. 60. The bucket has a velocity of 3.3 meters per second, 40 degrees south of east. South of what? East. South of what? One more time. South of what? What I'm saying is you draw the east first, because kids are still struggling with drawing these, and then go south of east. It's going to go east first, south of east. It's going to look like that, and it's going to go down at a 40-degree angle, not 43 degrees. Oh, and I can tell you how long that line is, too. It's going to be mass 20 times velocity 3.3. I can do this one in my head as well. Can you? What?
66.
Oh, thank you, Cliff. In previous, I've been debating this, Jordan. I kind of thought of this last night. So my previous, all the time, we just threw the momentum here. I'm sticking to calculations because I think some kids are wondering how I get those numbers. You could certainly do that as part of your showing your work. Since you're drawing a line, it's almost inviting you to write something next to the line as kind of like a label. You don't have to, but you certainly can. We've done the setup. Now to work. Bree, I'd like to add these two together. Oh, pray tell, how would I add these two vectors together? Hast thou a suggestion? Tip to tail, you say. Oh, you would be correct. I'll do it right here. I can do it. And again, let me encourage you, do a fairly big triangle. It doesn't have to be huge, huge, but if you're doing these, you're setting yourself up to make a mistake because your labels are going to start to run into each other. You'll read it wrong. You'll do something silly. So draw a fair-sized triangle. Give yourself room to breathe. Mine's going to look like this. 60. How long is the second arrow? How long is the second arrow compared to the first arrow? Tiny bit longer. You know what? I'll eyeball it. About-ish that. I've got a triangle that's at least reasonably close to scale. I'm willing to bet that angles that are bigger than 90 look like they're bigger than 90, and angles that are less than 90 look like they're less than 90. That's really what I want. I don't want to have an angle this big, solve for it, and have it tell me it's 119 degrees. Which then that would make me nervous. 66. So the resultant is that, and I guess that must be what the stone came in at. Yes? Good. Try the rest on your own. I'm going to do it slowly. If you get stuck, you can look up, but see if you can get the rest, the whole thing, all the way up to and including the direction. This is a job need for the cosine law, yes? So, what are we trying to find, kiddo? PSI, yep. Squared equals... Oh, wait a minute, Mr. Dueck. You forgot to put an angle in the triangle. That was silly. So let's see. It looks like that 66, when it's next to a horizontal line, forms a 40-degree angle to the right. How's that help? Oh, from 180? So this must be 140 degrees, right? Okay, now I'm better. And that's going to be what I know squared What else I know squared? Whoa. Come on. There we go. Try that again. Hit that instead. Oh, wow. Almost made that work out evenly. That would have been kind of cool. Is that? Yeah? Okay. Let's suppose instead of yucky angles, they were nice right angles, which would be easier because you could use SOHCAHTOA. What could I do to make this a bit tougher? Hint, hint, wink, wink, nudge, nudge. I could say something like this. Instead of saying find the initial speed, I could say find the change in kinetic energy. Good. What's change in anything? Wait a minute, Mr. Dueck, isn't the change in kinetic energy zero because isn't energy conserved? Total energy is conserved. Is kinetic energy conserved? Only in that magic, perfectly elastic collision, which we're kind of cooking the numbers to get it to happen. What's change in anything? So I think you could say this. Well, before the collision, what's moving? Both of them or just one of them? So that's going to be a half mass of the stone V stone initial squared. And no vectors, I don't care about direction or thetas or anything. That's going to be 0.5 times 12 times, oh, what I just figured out, 9.87 squared. How much kinetic energy was there before the collision? Now, the risk is, because I was making numbers up, we may suddenly find that the change in kinetic energy is negative, that somehow it gained energy, and if that's the case, I apologize for making up bad numbers, but I think I'm okay. 0.5 times 12 times 9.87 squared. Looks like we started out with 584.5 joules of kinetic energy. Wham! They collide. I think probably during the collision, some of that energy went into heat, sound, deforming the objects. Afterwards, what's moving? Mass 1, stone, bucket, or both? Both. Separate? Okay, so it's going to be a half mass of the stone, V stone final squared, plus a half mass of the bucket, V bucket final squared. 0.5, 12. What was V final of the stone?
5 meters to east.
Don't care about the direction. 5 squared plus 0.5. Mass of the bucket, which I think was 20. And 3.3. Who cares about the direction? It's a scalar, thankfully. Scared. Squared. A half times 12 times 5 squared plus a half times 20 times 3.3 squared. Oh, I hope this answer is... Let's find out. $258.9. Is that correct? $258.9. Yeah, this works because we lost kinetic energy. I should get a smaller answer, right? I think I said earlier that I didn't want the change in to be negative, and I misspoke. I do want the change in to be negative. I think during the collision we should have lost some kinetic energy. It's gone somewhere else. So let's find out. What did you say change in anything was? Final minus initial. So the change in kinetic energy would be final minus initial equals what? What'd you get, Cliff?
381.6.
Negative 382 if we go to 3, because it's our final answer, 3 sig figs. Or we lost 382 joules of kinetic energy. I thought energy was conserved. Yeah, total energy was. We didn't lose that energy. It got transformed into other stuff. Is it 382? I see people staring and looking with a frown on their face. Is that right? Is that right? All right, Dueck, better type this in. So what was it? 584.5 minus 258.9. I'm tempted to move you guys back there, or maybe back there you would have done it. I don't know. Is it 325.6? So 326? So
Oh, I see what.
Yeah, I totally care.
2.3.
Yeah, whatever. Oh, you did 2.3 for the velocity up here? Okay, so all of your numbers are wonky. Yeah. Okay, that's fine, because I'm the one that botched forgetting to change the numbers, so you can throw that right back at me. I don't think, Neve, on the test, I'd ask you to find a change in kinetic energy for a cosine law angles, but we handled it. But you know what? If it was a nice 90-degree angle, sure. Or even something as simple as just finding the final kinetic energy of one of the objects after the collision, sure. B. Example 2. Is that a collision? Is it angles? You know what? We've done that. I was going to do this one, but I was going to just change the numbers. But I think we're getting the hang of it. Really what I wanted to talk about today, believe it or not, is example 4, explosions. There's going to be an explosion on your test. It's going to be an explosion on your quiz. Sorry, I should be careful how I phrase that. You're going to have to calculate an explosion on your test. So some of you, that's a pretty scary test, Mr. Dueck. You're going to have to calculate or handle dealing with the physics of an explosion on your test. Your tests won't actually explode. Pardon me? Oh yeah, be an adventurous test, yeah. Now that would be a test. Wow. Okay. I'll even be more specific. You're going to get an explosion question on your quiz. I think on that one, I didn't make it a nice right angle, which makes it way tougher. But I think on your test, the explosion will be nice right angles and not so yucky. So we did this. Sadly, I gave you this same identical question with the same identical numbers. So you know what? Instead of adding 2, let's add 4s. So let's make that 6.4 kilograms. And let's make that cliff 14 meters per second. Six kilograms. 16.5 meters per second. And you know what? Let's make this fairly small. How about 2.1 kilograms? That should shoot it off pretty fast, I think. Because if the other big masses went in one direction. What's this question asking me to find? The speed of the third piece. And it's an explosion, which means it's a job for conservation momentum. By the way, how many of you ever, when you were a little kid, or maybe now, when you've been swimming outdoors and you try and stand on an inner tube, or you balance on an air mattress, or you balance on a rubber boat, you've tried that. If you tried jumping off, that's an explosion. It's a very slow explosion, but you may have noticed if you try and dive forwards, what happens to the floating object that you're standing on? Goes because momentum is conserved, but because it has so little mass, it almost always goes backwards faster than you wanted to dive forwards. Or, and I think I may have told you this story, but it bears repeating. I used to work at a summer camp, and I used to teach canoeing, and I would see people get out of the canoe like idiots. They would pull up beside the dock, they would stand up in the canoe, and then they would put one foot up on the dock. This is now an explosion, because they want their body to move that way, and their initial momentum was 0, so the final momentum still has to be 0, so the canoe is going to move that way. And I would just smile and watch them do the splits and tumble into the water, because that's a better way to teach them to never do it again. However, this was before everybody carried a cell phone, so you weren't worried about somebody falling into the water and having it be an expensive lesson. This is before people carried electronic devices in their pocket all the time. So, you know, even if they were wearing good clothes, you got wet, go change, dry off, and you'll learn never be an idiot. Now I probably, because I love technology, well, I might bring it. I might stop them from it. Maybe not. So just because it's an explosion doesn't mean it has to happen fast. What I really mean by an explosion is your initial momentum is 0, which logically means that your final momentum also has to be 0. Really? So This is a job for conservation of momentum. Before the explosion, what's the momentum? After the explosion, we do have three separate pieces. We have piece 1, piece 2, piece 3, each of which has their own momentum. Are there different directions and angles in this question? Yeah, because we also did look at, you may recall, a pop can explosion where things were nice and linear. One flew left, one flew right, which means you didn't need to do trig. You could just let one direction be positive, one direction be negative. In fact, the canoe story I just told you is very much of a nice linear, one goes left, one goes right explosion. When I asked you about balancing on a floating toy, that's also a fairly one goes forward, one goes backwards, linear explosion. But this one's got angles. You know what that means, don't you? Dulp, right? Momentum, oh, I've turned the page, and I think you all have too. I'm going to go north, draw a compass rose somewhere, southwest. Okay. Piece 1, momentum 1. What direction does it fly off at? Read the question. There's audience participation here, boys and girls. How big? Well, its mass is 6.4. Its velocity is 14. I guess I'll let you use a calculator for that one, Cliff, assuming you type it in right. Hey, what is 6.4 times 14? And don't round off, because I'm going to be using this. So carry. What is 6.4 times 14?
89.6.
Even? The second piece, direction. East. Momentum, 6 times 16.5. That I think I can do in my head. 6 times 16 is 96. 99? Double check me. Is it? No, the whole thing, 99, right? Right? What makes it an explosion race? What's my initial momentum? What's my final momentum? How's that going to look when I draw a triangle? And this is the most common mistake. Kids get this, and they draw the triangle wrong because they're so used to adding everything tip to tail and drawing a resultant. Here, it's going to be tip to tail, but ending up back where you started from, because that's what 0 looks like as a vector diagram. Here, it's going to look like this. North, east, and there's the resultant. There's momentum 3. Because you want it, Petra, end up back where you... That's a definition of 0, right? If that was a displacement, that would be 0 because you ended up back where you started from. Is that okay? Well, again, most common mistake, kids draw from here to here. They get the right magnitude, wrong direction. I said to you this. On your test, I'll give you a nice right angle like this one. I think on the take-home quiz, I gave you what of what's and what of what's, which gives you a more challenging triangle that you have to use the sine law and the cosine law, because I think, correct me if I'm wrong, that's something still people need practice with, so I'm trying to flog that as much as I can. Here, though, Pythagoras. By the way, it's actually the cosine law, not Pythagoras. Don't write this down. It's actually this squared equals this squared plus this squared minus 2 times 89.6 times 99 cosine of, hey, how big is that angle? But do you know what the cosine of 90 degrees is? Turns out Pythagoras is a special case of the cosine law. I don't know if you guys knew that, but nerd moment. Yeah, big deal, Dueck. Oh, shut up. Momentum of object 3, 89.6. Whoop. Come on. Plus 99 squared, square root. Final momentum, 133.526. How can I turn that into a velocity? Take that 133.526 and divide by 2.1. 63.6 meters per second at, look where your vector is starting from. It's starting from right here. And thankfully, no sine law, that 89.6, opposite adjacent to hypotenuse. Opposite, adjacent, you know what? Tan theta is going to be 89.6 over 99. So the inverse tan of 89.6 over 99 is going to give me a lovely 42-degree angle. What of what? North of south, east of west, what of what? South of west, yes. 42.1 degrees. How else, what other little curveballs could I throw at you as a part B? Hey, I could ask you how much energy was contained in the explosive. Find the kinetic energy of the first piece, the kinetic energy of the second piece, the kinetic energy of the third piece. And the nice thing is, Race, that's fairly plug and chug. No angles required. You'd have to go through this to get that velocity, but then it'd be a half mv squared plus a half mv squared plus a half mv squared. I guess that would tell you how much energy was contained in the explosive. That's kind of cool. Or I could just say how much kinetic energy does one piece have. Could do that. Is that all right? Example 5 we did last day. We did a question where there was a roller coaster colliding because there is a roller coaster with an initial velocity rolling down a height, change in height, that's a job for energy. Wham, they collide, change in speed, that's a job for momentum because there was a collision. Rolling up the next hill, that's a job for conservation of energy. I'm not going to bother doing it. Nasty scholarship question I'm not going to bother doing. It says finished unit, complete the whole review, and also I'm going to give you 45 minutes to work on this stuff. Now, on Monday, we're going to go over the work energy test. We haven't yet, but that would be a good time to go over it since work and energy is also appearing on this test in combination questions. Boy, when is your test going to be? Probably the following Monday. I don't like doing tests after a weekend, but that's probably what I'm going to be stuck with. So I'll probably do a tutorial later on that week. The only problem is it's also air show week. Ugh. Oh, you know what? I'll give you more information as we look and see how next week fleshes out. So let me give you the take-home quiz.